Great. Okay, so welcome everybody to today's Friday noon talk, McGill Medical Physics. Our speaker today is Dr. Teodor Stanescu from Princess Margaret Hospital, University of Toronto, Techna Institute, and other affiliated institutions. Dr. Stanescu is a medical physicist in radiation medicine program at Princess Margaret Cancer Center. That's his primary affiliation. And he arrived there from the University of Alberta, in fact, where he completed his PhD at the Cross Cancer Center and then did residency training at the same place. And he is board certified in radiation therapy. And he's one of the therapy physicists around Canada who's active both in therapy and in imaging and applications of imaging. So he really works at an interesting cross-section of both research and clinical work. His primary area of research is in that area, in image-guided radiation therapy. He has worked on a number of different projects on adapting MR to the radiation therapy world, introducing MR to therapy planning. He designs, develops, and integrates imaging techniques and therapy equipment and creates very interesting solutions to the ever-growing number of challenges we might come across in radiation oncology. So today, Dr. Stanescu is going to talk to us about his work in reinforced adaptive MRI-guided radiation therapy. So, welcome.
Thank you very much. You can hear me, right? Perfect. Okay, hi everyone. So today I will present some of the exciting work that we've been doing related to MRI-guided radiation therapy. This is our research team, as well as local and external collaborators. So the main motivation for the work is to move towards full MRI guidance in radiation therapy, in particular for upper GI cancer. Cone beam is definitely not sufficient to resolve image contrast and motion for either the targets or the surrounding OARs. I really believe that we need to develop new tools in collaboration with the industry to facilitate deeper integration of MRI and RT. And as medical physicists, I think we have an important role to play here. So one of the projects that we've been pushing forward is on the design and validation of a comprehensive phantom for the quantification of spatial image accuracy in MRI. This work is done in collaboration with Modus Medical off of Ontario, Canada. So system and scan-related distortions are due to two main factors. B-naught inhomogeneities, so these are issues related to the main polarizing field of the magnet, being 1.5 Tesla or 2 Tesla, and issues related to the imaging gradient nonlinearities. And these two types of problems are typically tackled with separate techniques. So very briefly, image or B-naught inhomogeneities are typically done in homogeneity phantoms. They can be 3D or 2D, small field, large field. Kind of the bottom line is that you want to measure some phase images, and from there you want to derive some B-naught distributions. And this type of test is still mostly framed as a servicing test rather than a QA measurement relevant for radiation therapy. The second one is a bit more subtle. It involves imaging gradients. So here, this equation shows kind of a quick summary of what is expected to see in the B field. So you have the ideal, let's say 1.5 Tesla field with no issues. Then you have some perturbation in that homogeneity, of that field, and then the susceptibility artifacts due to the presence of the sample, whatever we image in the field. So back in the 90s, Gisard et al. Came up with a nice methodology, very simple to kind of resolve the issue with gradient-related image artifacts. So for same phantom setup, you acquire two scans. All the parameters are the same, with the exception of the polarity of the readout gradient. And applying simple algebra, you can isolate the effect of this GNL. So. But like part of that process is that you also extract the combined effect of B-naught and susceptibility. So, but most of the time this is like a throwaway data, because you cannot really distinguish between these two coefficients. So to measure this type of distortions, there are many designs proposed in the literature. The processing algorithm is largely the same. So you acquire some image data, you derive some control points in those images, you align them to a template, and you resolve these local vector fields, and then you plot your distortion maps. So in this project, we really wanted to simplify that process, and with a single phantom, a single simplified imaging procedure, we want to measure pretty much everything that we want and that's relevant for radiation therapy. This is a bit complicated because there are many factors that are involved in the design of such a phantom that can derail the effort. So the approach that we took was to kind of link spatial perturbations with the property of magnetic field, and this kind of made sense because those distortions or spatial inaccuracies are related to perturbation in the main magnetic field. So we defined what's called direct problem. So solving a class equation with boundary conditions. We measured only at the boundary of this particular phantom shown here to your left. So we define this type of problem for two different domains: for the inside of this boundary condition and also for the outside of the boundary condition. And then you can solve these problems at two separate steps, and you can reconstruct the vector field for the entire volume of interest. So we published this work in medical physics a while back, and we demonstrated that in different quadratic geometries, this interior boundary problem stands. We also look at, and these are rather small volumes, but we also extend the analysis for an kind of arbitrary shaped volume. So this is a large phantom that was imaged, and this is what you see here is the actual field of view that you can resolve with a phantom inside the magnet we used for that experiment. So at this point in time, we are exploring the problem outside the footprint of the phantom. This is a bit more challenging, and we have to do a bit more tweaking in order to identify the validity of that methodology. The preliminary data shows that we can expand the analysis, but more work is required in this space. So at this point in time, we're happy with the methodology for resolving the general component of the distortion field using this phantom. So then we said, okay, well, this is the data that we subtract from those two measurements. So we said, okay, well, we need to resolve this coupling in order to be able to save the B0 component, which is variable. The susceptibility component is coming from the phantom. It's just the geometry, the design, and the materials used in that particular design. So to tackle this problem, we again solve matrix equations, but with slightly different methodology based on finite difference methods. So we created a CAD design of the phantom, and we digitize it. So this is kind of a different cross sections to the phantom. We solve again magnetic field with magnetic field simulations, and we generated these maps relevant to the design. And as you can see, there is a lot of effect in the middle of the phantom, but the majority of the effects are on the end plates of the phantom. So this slide, for example, here corresponds to one of the end plates of the phantom. Further, we say, okay, well, this is defined on the boundary of the phantom. So this, you can use it as a boundary condition and resolve again a harmonic analysis problem. And you can kind of look here in this picture how this type of susceptibility effects expand inside the volume of interest. So this is the type of extra distortion that you expect to see in this measurement if the susceptibility effects are not corrected. So we validated this kind of process using data from multiple scanners. Here I show only 7 MR scanners. So black lines or dots correspond to the combined effect of B0 and susceptibility. And after removing the susceptibility signature of the phantom, we end up with the gray data, which is representative for the clean B0 map of that particular scanner. And this was validated against magnet specifications and also data measurement data available in the literature. So at this point in time, we're happy with the phantom. We say, okay, well, the phantom gives us all the information that we need with regard to the system-related distortions. The second factor that you see in the MRI images when you analyze the patient data is the susceptibility effect induced by that anatomy. So back in the 70s, Aludeke presented this nice paper and explained the susceptibility artifacts in MRI imaging. So this is a kind of a simple experiment with a simple phantom. We have two different materials, air in the middle and water on the outside. And for 3T, you can see how the shape, the rounded shape or the round cross section of the phantom is altered by just varying one of the parameters, which is the reductive gradient. So this is always the case in patient data, but it also depends on how you scan those particular patients. So the approach that we took was, okay, well, you can do experimentals and you can do measurements, you can acquire extra data and post-process and kind of collect all data. But we said, okay, well, I think it's easier if we just look at the envelope of these effects and try to optimize the imaging protocol rather than adding more complexity to the workflow. So in this case, we look at the CT data and we mimic on the CT data, and we pick CT data because it's spatially accurate. And again, we run the same type of analysis that we run in the Phantom in order to simulate the effect of these distortions. And we did this in different types of anatomies and from brain to pelvis. And we also look at different configurations of the B field, which are specific to the MR-Linac systems available out there. So this one, for example, would correspond to a cylindrical bore magnet, conventional design. So B not along the Z-axis, the long length of the bore, and this is for the geometry, which is specific to the Alberta MR-Linac design, where you have a rotating biplanar magnet elongation. So we also did in the MRI experiment we acquire static data 3D, so that we that's what I showed here in the previous slide. But we also do fast imaging and motion imaging, right? So we want to look at these effects in that context as well. So this is kind of the worst case scenario that we would expect: a small target in the lung, moving supine for about 2 centimeters, and this is kind of getting closer to what's relevant in upper GI, in particular for liver. So we map these effects. We also combine them. We look at the composite effect of these effects. So we look at the susceptibility-induced effects and also the system-related kind of artifacts induced by or introduced by the system. And then we map out kind of the composite distortions for these scenarios for different configurations. So then, when it came to implementing the new procedure on the MR-Linac, we applied this to liver. So we kind of we took the methodology that we developed previously and applied to this particular site. So this, I'm showing here the system-related distortions, measure the phantom projected on the anatomy. So this is kind of the dome of the diaphragm, so interface between liver and lung. And this is the expected susceptibility effects on the same geometry. And we found that the distortions are typically within like 1.5 to 2 millimeters, which is reasonable given that the best resolution that we have in this imaging on the MRI is in the same range. So the next step was, okay, so we are happy with what we achieved in terms of spatial accuracy on the imaging. We also want to look at the combined spatial and temporal accuracy of fast imaging that we need to acquire particularly in upper GI in order to resolve motion. So we partnered with CRS and we started to look at the design of their 4D MR Phantom. So this is a kind of an interesting device. You have a static component with a number of anatomical elements. Here you see kind of a cross section on MR and CT, so it's dual image modality. The Phantom also has this movable cylinder with a tumor inserted inside, so you can create different contrast. The cylinder can move 1D supine, but it can also rotate, so it gives you a 4D type of motion profile. You can also program this Phantom, and you can use something that's simple like a sinusoid or something that you want to program yourself. So the MRL TSM workflow allows, so the MRL workflow, what's called TSM workflow, allows motion monitoring only with one 2D sequence, which is a bit unfortunate. And we very quickly realized that, and this is actually shown here. So we very quickly realized that, this sequence is not what we want in liver, because in most of the cases, we don't see the target. So we had to develop additional sequences that T1 and T2 weighted in order to complement our MRI workflows. So we use this Phantom in order to investigate the kind of the properties of these particular sequences. But in this particular case, the Phantom was programmed with a sinusoid. since we plan to do all our treatments in Excel, and I'm going to get to that in the next slides, we knew that we will need to acquire these 3D navigated trigger sequences. So these are kind of so these sequences acquire data only when the anatomy is in a certain phase of the respiratory cycle, in particular exhale. So we had to verify that the data acquisition, bidding, and construction are in the correct format. The navigated parameters were also tested for optimal data acquisition. Here we show the representation of a 4D MR phantom in the axial, sagittal, and coronal views for 3 distinct scenarios. So in green, we have kind of the no motion case. Here we have a kind of an average acquisition with some motion applied to phantom, and this is data that you could potentially acquire in Excel. So that way, that was kind of a nice analysis and a comparison of different acquisition modes. So this is kind of a quick roadmap of the MRL at our institution. After system commissioning that happened back in September 2019, we initiated the first liver SBRT treatments in March 2020, so about a year ago. Our first pancreas patient got treated earlier this month, so almost a year later. Currently, more sites such as bladder, kidney, anal canal at various stages of development. So early in the process, we built a multidisciplinary team of medical physicists, MR, RT, cross-trained radiation therapists, and radiation oncologists. We went through a comprehensive clinical work for development and validation, since MR guidance was very different than our conventional process based on chrome beam IGRT. So we did extensive phantom work to build, optimize, and stress test these workflows. And prior to the clinical release of liver as a clinical site on the MRL, we did 40 full live driver runs on healthier patient volunteers. So on a conventional LINAC, we've been using several dose levels to treat liver SBRT, ranging from 2750 to 6,000 centigrade in 5 fractions. So specific to liver, there are 3 key challenges that we need to take into account. So soft tissue contrast, obviously, is needed to visualize the target and the surrounding OARs. We need to manage the organ motion, which can be anywhere from millimeters to centimeters. And lastly, we always expect significant interfraction changes in the OARs. And this is directly affecting our ability to adapt the treatments and achieve predefined clinical goals. So the complexity and robustness of the liver SBRT procedure is highly dependent on how well we can manage these challenges. So for commissioning, we took a kind of a 2-step approach based on the imaging and the online adaptive workflows. So we already discussed the spatial and temporal variation of this workflow in terms of 3D and 2D imaging, and also 2D for motion. So we used all those phantoms to tackle those parts of the commissioning process. So once we identified kind of what are the pros and cons of the imaging, we went into the development of the treatment workflow. The imaging was embedded and further optimized to provide the best image quality for contouring, and with the least penalty in terms of acquisition time, resolution, and contrast. So sub-processes were also developed and tested and validated for the online adaptive strategies, delivery, patient-specific QC, and ultimately end-to-end testing. So in liver, we typically sort our patient into 3 categories, depending on the method that we use, right? So the first option is to do ABC, and this is our preferred choice, and because it leads to the best cone beam imaging and smallest treatment margins on the standard LINAC. However, only half of the patients, roughly half of the patients, can tolerate ABC, and then free bleeding under compression becomes the second option. About 5% of the cases cannot do ABC and AC, and they have to be treated in free bleeding. For MR guidance, or for MRL, we decided to treat only in compression, and this is one of the devices that we use. One thing to note, different from these images, is that we don't do arms up. On standard LINAC, we do arms up. The sessions take around 20 to 30 minutes, but on the MRL, we do our arms down because the procedures are much longer, about double that, so around 60 minutes. So the compression belt wraps around the patient and applies pressure via an inflatable cushion. You can see it here in light blue. this is the vertebral belt, you have markings, you have a support plate, cushion, and then you inflate it via this hand pump. On the MRI, we allow up to 1.5 centimeter under compression as residual motion. So our gold standard imaging workflow relies on the acquisition of both CT and 3T MR scene data with contrast agent. So the venous and anterior phases are acquired in volunteer breath hold. For non-ABC cases, 40 CT is also required to have defined the envelope of target motion and ITD emojis. For 3T MR, we do both T1 and T2 imaging, and we also quantify the motion using 2D CNET. All this 3D data is important to RayStation, our main treatment planning system, and it's pretty much co-registered and help to define the contours and clinical intent. For the MRL, though, the workflow is a bit different. So we start at the MRL, and then we move to CTMR and CTC. So first we acquire like some 2D CNET sequences in order to quantify the residual motion under compression and to assess the overall patient setup stability and to make sure that the patient qualifies for the MRL. Secondly, we acquire 3D respiratory trigger scans or average scans depending on the amount of motion that we have in the setup. And again, this is the data that we need to plan on. Then we, once we collect all the scene data, we prepare what's called a reference plan for the MRL, which is specific to that particular platform. And we use it as a baseline for the MRL online adaptive workflow. This diagram here is a bit busy, but it shows kind of a condensed view of the key processes involved in our liver MRL workflow. So in addition to the conventional RT setup for SIEM and planning and plan QA, we have the full online adaptive process. So we replace the combing matching with a full replanning activity. In the past, we used to have a kind of a day zero kind of dry run session prior to engaging in the treatment delivery process. And this was actually necessary to resolve all the mechanics of the workflow, but we kind of gave up on that one because we gained enough experience and be confident that we can go straight into treatment once we have a reference plan. Unique to MR guidance, we have the ATS process or the adapt to shape process, which involves the formal registration between live MR data and reference data. So contours are subsequently propagated and refined, followed by plan optimization and evaluation. So another important aspect of this workflow development in QA is the end-to-end testing, which involves all the workflow mechanics in one go. So for end-to-end testing, again, we heavily use the 4D MR Phantom. We use it in two modes: 3D with no motion, just by changing the cylinder rotation or positioning and kind of replanning for each session, or using 4D, the full 4D functionality with motion activated. So this is a typical example that shows our testing process. So plan is prepared, you have the CT. So this is kind of an old slide. Initially we started with a CT as a as our standard imaging procedure for planning, and now we moved to full MR. So again, reference CT or reference MR. So we prepare the anatomy, we have a reference plan, and the day of or subsequent experiment, we modify the geometry of that setup, and then we pretty much adapt the contours and generate new plans and try to achieve the clinical goal that we define at the reference stage. So this is kind of a registration between the two different setups, extreme setups, mimicked on the 4D Phantom, and obviously motion can be applied to Phantom in order to test the MRI motion monitoring. So while we plan and maintain a certain kind of a envelope of parameters, we can also turn on the motion and see if what the process will look like with the motion engaged. The online treatment sessions rely on the adapt to shape approach. Again, this means a full replan activity. The workflow also provides an ATP or adapt to position setup, but I'm not going to go into that because it's not necessarily applicable to upper GI sites. Density override has to happen, especially if you plan on the MR. And typical plans are done with MRT 10 to 12 fields. Secondary image calculations are done in Ray Station, and the whole treatment session takes about an hour. Regarding online contouring, to speed up the process, we look at only an area of about 2 to 3 centimeters around the PTV. And the main reason for this is that you want to decrease the overall session time, but also most of the OARs are those points, so we don't need to contour for organs in order to quantify the quality of the plan. This slide shows a liver patient volunteer example. So here we have the actual cone beam acquired on this patient. The patient, I believe it was, the patient was treated for one fraction of the cone beam, and then we move him to the MRL for additional imaging. So we have the CT, the planning CT, and here we have the T2-weighted, T2 navigator triggered sequence. So here at the bottom shows kind of the sequence that's generated while the data is acquired on the scanner. It's hard to see here, but there are some kind of green dots at the bottom which show kind of the instances where when the data was acquired for this particular scan. So this scan was acquired in the X-ray phase of that motion. So the same patient. So again, this is the planning MR data, and here we have kind of some examples from the process of testing different CNS sequences. So this is here at the bottom. You see the sequence that's used in motion monitoring. So in this case, the target is between the boundaries of the liver. So you can kind of use the boundary of the liver as a surrogate, but you don't really see, you don't really have any other information on the target. These are the sequences that we were testing at the time offline, not through the Elekta workflow. This is a T2, you don't really see the target, but on these two T1 sequences, you can actually delineate and nicely see the target. This is another case. Again, this is for motion monitoring, and you see these shaky videos because these were actually recorded on my phone. This is not necessarily available as data for post-processing work to move it outside the system, so it's not easily available. It's not like generated as you normally see it on the scanner. And these are the corresponding T2 and T1 wave sequences for this particular case. Another one, this is one of the first ones. We didn't have those extras available at the time. Again, big mass. Really, this sequence is not helping us in any way. I mean, you see this kind of boundary here of the liver and see how it's moving, but you don't really have much information inside the liver. Okay, so this is some extra information. This is work that we did in pancreas. So on standard LINAC, we don't compress these patients. So we went to, so in this experiment, I mean, we did a number of experiments, both in patients and healthy volunteers. So in this particular case, we look at motion on the dome, motion on the liver, so was about 17 millimeters with no compression, 7 on pancreas. After applying compression, you go down to 8 on liver and 4 on pancreas. So it makes a huge difference when you apply compression. The kind of the historic argument for not using compression in pancreas is that you bring the immunostructure close to the target, so it makes it harder to achieve a plan on standard LINAC. And that's likely the case, or I think it's a true assumption, especially on the combing where you don't actually see the pancreas in most of the cases. This is another example from, I think, from the same one. So this is a healthy volunteer, but what I want to show you is here at on the lower right side of the slide. So this is kind of what we ended up using. So this is actually what's in our critical right now. So we developed another sequence, high-res in plane, and again showing no abdominal compression. With compression, you can nicely see the anatomy delineated. So this is the type of sequence that we currently use for our pancreas cases, or even liver if the motion is smaller, like around 5 millimeters. Okay, this is a busy slide, but I'll try to kind of go through all the little details. So this is kind of the workflow, and you can also hear the timing for each of these steps in the process. So if you sum them up, you end up to about like 60 minutes. So that's kind of our average time for a liver or pancreas treatment procedure. So we start here, patient setup, compression, again, arms down, not arms up. We do a scout. We check a couple of things on the scout, and then we do cine sequences on the dome. So the dome is important in particular for liver, because it's an indication of how well we establish the same setup that we planned for. If we're not happy with the setup, if there is too much motion, then we go back to the room, we apply more compression, and we iterate. In a year of over the past year, we had to do this, I believe, only once. Most of the time, the setups are pretty robust. We record the maximum on the belt and also the pressure on the pump. So the setups are pretty robust. Then, once the setup was checked, we go into 2D cine on the target. So this is actually a nice check to confirm that the ITD margin that we plan for are indeed applicable to that particular tumor fraction. The next step, 3D acquisition. So depending on how much motion we have in the workflow, we have these two different streams. So less than 5 millimeters, we go average. More than 5, we go with triggered scans. Then data is transferred from the MR console to online Monaco. This takes a while. Data is co-registered, and contouring can start. Once we have the GTV contoured, we can turn on motion monitoring to see how the target sits within our ITD margin or PTV margin. So if you can see here, the green contour is our PTV. If you can see the target. And then finalize contours and go into the planning, optimize the plan. Once we achieve a good plan, then we go into plan QC. So this is kind of a standard process, but it's all condensed in 1 hour. In between these activities, we also acquire an additional scan offline, and we overlay this extra image, the same sequence that we acquired at the beginning of the session. We want to kind of do a quick check on the GTV to make sure that it didn't move more than it was allowed. And if everything goes well, then we beam on. And while we beam on, we can acquire another 3D scan to kind of look at the image data while we deliver. And we can also, again, motion monitor the anatomy. So if you pay attention to the timelines, you can see that between the first scan that we use to generate a plan and to treat with, there's a gap of anywhere from 40 to 50 minutes between. So this point, first acquisition, and the beam on, the last acquisition. So obviously, we have redundancy checks to make sure that we have a good control over the setup. Target doesn't move beyond the ITD margins, but again, we don't have a good like a full picture of, for example, what's happening with the OARs. So what we end up with is something like this. So we have the reference plan. We never use this one actually to treat in this workflow. So it's more like a requirement for the workflow, just to be able to engage into the online activities. And then we have 5 fractions. So these are imaging acquired at the beginning of the session. We generate a plan on them. Then we do this verification. We check the GTV, P, or GTVs, to make sure that they're in the right spot. And then we acquire these extra imaging during beam on. So this kind of brings us to the point of the title of my presentation, which is reinforced adaptive radiation therapy. So this is fine. So this is adaptive radiation therapy. We adapt on each fraction. We compute the dose of the day. We have these delays in terms of when you plan and when you treat, but we can manage that to some extent. But really, the system doesn't really allow you to do more than this. You have to really define everything at the beginning, and you kind of stick to that plan. So you define your prescription and you define your clinical goals, and for each fraction you have so much. You have like a threshold of how much clinical goal, how much room you have in each clinical goal, but you're stuck to that approach, right? So we want to push it a bit further. So we said, okay, well, if I have my first fraction here, there's this gap of 40 to 50 minutes. We said, okay, well, let's assess what the dose is on the actual imaging that was done during beam on. So we bring the data. So Monaco doesn't necessarily allow us to do this in a kind of a nice way. By the way, we want to automate the whole process, so this is not possible in Monaco. So we bring all the data into RayStation. So RayStation, by definition, allows us to do. It's very flexible. It allows us to do a lot of scripting, automation. So it's a kind of nice environment to do this type of exercise. So we bring the data in, so we bring both data sets, those cloud and ROIs into RayStation. We do a first registration. There's some change here in the anatomy between the two time points. We do a deformable, and then we work or deform the dose from the ATS plan to the BMON data set. And then we look at the dose difference and the clinical goals, and we generate a report. So this is pretty much kind of a quick assessment, and this can be done in within minutes, right after the end of the treatment. And this again, we haven't implemented this yet in the clinic. This is kind of still work in progress, but this is more like the concepts that we're working on. And again, we can do this for each of these 5 fractions. You generate a report minutes after you finish the treatment to give you an indication of how well you delivered that treatment. But then, we want to push it even further. So, we have this quick assessment, which is great. But this doesn't tell us, how much room we can save in each clinical goal. So, for example, if we started the first fraction, we can look at the plan or the data set that we have used for delivery, or we can generate through those deform registration another kind of plan on the BMON data set. So we look at the so now we don't look at the data within that session, but we look at the data back at the reference stage, like how we plan this case. So we compute the difference, the delta between the reference plan and whatever we delivered on that particular day. So we compute kind of we assess how much room we have left given the constraints and penalties of that particular day. And then, when we do fraction 2, we start summing up the dose from those plans. And again, we compute the clinical goals room that we have left for the next 3 fractions. And this is, I think, very valuable for us, especially in upper GI, because OARs move all the time. So, one day you might have the large bowel into the field, another day it might move away centimeters. So, but in the workflow that we have on the MRI platform right now, you're stuck with whatever kind of fixed threshold that you have available for that particular session. So this is giving us a bit more room to change, to potentially escalate the dose, reduce margins, and so on. And so on. We do this to pretty much from fraction to fraction, and we compute these clinical goals of each fraction, and we implement them as a template in the next fraction. When you go to fraction 5, you pretty much sum up everything based on whatever data set you want, like the full data set or the one under BMON, and you provide a final report to see how well you delivered. So again, work in progress. So this is done by Teodor and Alex, shown here. One of them is physics resident, another one is a master student working with us on this project. So this is kind of a GUI interface that we came up with. So this is allowing to do partial sums. So for example, two fractions and compute these clinical goals, or you can do like total sum, or looking at the whole treatment. So you can accumulate on whatever data set you want. You can go back to fraction 1, you can go back to the reference stage, or you can do even a forward accumulation on these plans. The key aspect of this process, I think everything relies on how good your deform registration is, right? Because everything is going to be deformed, everything is going to be quantified via that deform registration. So in RayStation, we have different tools to do that. So we can do image intensity, we can do ROI based, a combination of the two, and we also have a fourth option of biomechanical modeling. We can also define what was the envelope for the deform registration, because we want to do it locally. We don't want to do it on the whole image if we don't do it image intensity. So that we kind of try to push it hard in the region that matters. So we can define a certain envelope of that deform registration, and then we can run a single type of deform registration or multiple. We can rank them and provide a report and generate these clinical goals that can be used from fraction to fraction. So we hope to do this in an automated fashion. So this was already complicated, but this is not. It can be worse than that. So this is one of the cases that we treated about a month ago. So 2 lesions. I mean, they're further apart. So we had certain limitation in the protocol that we had and other things. So we ended up with 2 different plans, one for each lesion. Obviously, we pay attention to how these 2 plans are coupled, but again, this is like very complicated already. So you have like 10 plans, 5 fractions for each. I think this patient was treated on separate days, or most of the fractions were done actually the same day, back to back. So, once one lesion was delivered, patient took a break, 1 or 2 hours, and came back. We did another session. So applying that formalism that I just described in terms of how you accumulate this is much more complicated in this case, because you can accumulate each plan longitudinally, or you can start combining the plans for each fraction. Arguably, you could potentially treat this patient with a single plan, but then you have problem in terms, you could potentially run into problems in terms of deformation and location of the target, so you might not be able to actually hit both lesions with one plan with the same smaller margins. So kind of to wrap up, so we want to consolidate and deploy clinically this reinforced radiation therapy or adaptive radiation therapy methodology. So that's kind of our push right now to introduce these automated tools into clinic. We're also looking at functional imaging. We've been collecting the WI imaging data, which is the sequences available on the Unity platform. We also want to kind of link that scanner with our 3T. And we aim to look at some new dose fading strategies. But again, this is largely work in progress. We still have to do a lot of work in terms of calibrating these sequences. 4DMR is also now on our radar with some early collaboration with UMC, and we're looking to get some funding, to pull this project forward. Again, this will help us explore different strategies of planning, looking mid position, motion trading, and so on. Another focus is to push esophagus on this platform as well, which is a bit more challenging because we don't do SBRT in this site, and we also don't require MR at the same stage. So it brings other challenges to the table. So before I conclude, I just want to show you like 2 quick slides. Other projects that we've been working on, I mean, they're not related to upper GI. So this is a CT stuff that we've been doing in CNS and head and neck. It is in cyclogram, and we hope to use this methodology into upper GI to help us with the CD number or count-free unit maps. We've seen some variations in some certain scenarios, so we'd like to improve those calculations with this kind of approach. And another kind of last slide. So this is a project which is again in parallel with the MR developments. So this is a collaboration with MIT and Global Research, Global Research. So we're looking at kind of a novel design for an MR-Linac, and this project was funded recently for 2 years, and we hope to show you more results next time. Thank you very much.